at them. I need about 15-ish minutes probably. You need to write down some of these details as they are relevant for some free response questions that you guys are working on very soon. Okay, so we already knew Coulomb's law. We've seen it about 3 times. I'm not showing it to you 3 times just because it's really important. You'll be using that to try to accommodate or try to explain some of the attractions and repulsions that you'll continually see, especially in terms of energy. So force, F, force, does refer to force of attraction or force of repulsion. So who's got ionization energy? What group has ionization energy? You're like, not us? Thanks. So you guys should know if you have ionization energy. Who is it? With confidence. Okay, raise your hand, thank you. So yes, you guys will be talking about electron-electron repulsion. Well, if electrons are far away, are they going to repel? Not really. They're far away. If they're close, their force of repulsion will be quite high, and that's because of the distance component to Coulomb's law. So there's a direct relationship between charges and force, especially if they're opposite charges, aka electrostatic attraction, opposites attract, and there's an indirect relationship with distance, or the proximity that these charged particles have to each other. So being able to put Coulomb's law in words is more important than being able to calculate Coulomb's law. Like, I don't think we'll calculate actually the force of attraction ever, but it's about the relationships of those variables. Does that make sense? Qualitatively explaining it. Okay, so one factor that Coulomb's law does help with explaining is lattice energy. So lattice energy is the energy that it takes to break a crystalline structure. Crystalline structure, give me an example. Crystalline ionic lattice structure. Give me the salts, everything ionic. I need specifics.
Copper.
Copper what? It's got to be ionic, right? Copper is a metallic lattice. Give me an ion. Copper 2 chloride. Okay, so copper 2 chloride. Sorry, I was waiting for the whole shebang. So how is this lattice structure arranged? What's the relative number of atoms here of each? For every 1 copper, you have 2 chlorines. And it's going to repeat. Chlorine, chlorine, copper. Okay, so there's going to be an arrangement that allows for this lattice to kind of form with the appropriate number of the ratio that it should take on. I just need this space right here, so I'm going to erase this. So there's a lattice. Now that doesn't just break apart with no energy. It's going to take some energy, aka called the lattice energy, that would take to break that crystalline structure. But the energy will vary based on 2 factors. 1, how big are the ions? 2, what are the charges of those ions? So you should be able to do a relative comparison of the energy it takes to form or break this crystal based on size of their charges. And the sizes of the charges play in because, thank you. All right, so the charges play into the charge component up here. So would you say, just based on charge, magnesium oxide or sodium oxide would have a higher force of attraction? Magnesium oxide or sodium oxide? You might write down the formulas if you need to. Why? Okay, so it has a higher charge. Give me more.
So the electrostatic attraction is stronger.
Why?
Because like the charges are greater.
Because the charges are a greater magnitude is what I would say. Okay, so the higher the magnitude, the individual charges, the higher the charge product. Do you guys remember doing charge product at all? Charge product means, like, what does product mean in math? Multiplication, right? So we're multiplying the charges. That's exactly what we're doing here. So a 2 plus for magnesium and a 2 minus for oxygen would yield a 4, I know it's a negative, but a 4 overall charge product, versus sodium oxide would have a 1 plus for sodium and a 2 minus for oxygen would have an overall 2. So this higher magnitude of the charge product, that's how you should say it, charge product, yields a greater force of attraction versus the 2, which is a lesser force of attraction. Good so far? Okay, now then you could talk, I mean, this is just some extra examples. Then you could talk about the radius. Who's my ionic radius group? Okay, so you guys will be talking about cations, anions, and their differences, and how do they differ from the parent atoms. But then overall, we have an atomic radius group that's going to give us the holistic picture, not ion form. But still, give me an example of a huge atom. What atom on the periodic table? Francium. So francium. Well, what kind of ionic compound? Give me an example of francium in the ionic compound. Francium bromide. Okay, so francium bromide. So then you have francium, and how big is bromine?
I mean, not like
Medium-ish. Okay, so francium bromide versus, let's do, yeah, we can do lithium. Lithium fluoride. Okay, there's going to be a difference in teeny tiny. There's going to be a difference in their atomic radii, which would then cause their nuclei or their electrons surrounding the nucleus to differ in level of attraction. So what you then would say is, actually, let me compare the same ones. It's easier if you have a constant. So let's do francium fluoride. Okay, so who do you think would have a greater force of attraction between the ions? Why?
just the distance between the nucleus of lithium and its outer electrons is smaller than francium's.
Right, and so within lithium, the lithium positive nucleus is what's attracting to the fluorine's ion, or electron cloud. Same difference on the other side. Fluorine's nucleus is attracting to the electrons on the other side. So the closer they are, the stronger the attraction. And you explain that because of the inverse relationship that distance has with force of attraction. So the farther away they are, the nucleus doesn't attract as quite as much, so this would be an easier ionic bond to break than that one would be. Meaning, who requires more energy to break the lattice? Say again? Lithium fluoride require more energy because it's got a better attraction because of its closer proximity of the nucleus to the electron cloud. Shake your heads if you're okay. All right, so that is the application of Coulombic attraction, kind of in all. So let's talk about lattice energy a little bit more. Oh, sorry, fun fact. Whenever you're trying to qualitatively explain this, the charge product is much more important to talk about. If you can compare them, like for example that 4 versus the 2, that's going to be your kind of winning explanation. If you have to express anything about ionic radius, it's a little bit trickier because as our group with ionic radius will explain, it's not 100% a trend. You're going to have some differences. So you're definitely going to explain things with charge factor more than the radius if you can. All right, so then lattice energy, these are some examples. So we just did lithium fluoride, right? Lattice energy is over 1,000. I don't have francium fluoride up here, but let's compare it to another fluoride. Here is potassium fluoride. Why is potassium fluoride's lattice energy 800 versus lithium fluoride's is over 1,000? Raise your hand when you're ready. Courtney. So to explain that fully to get all your points, you would say
potassium has the bigger ionic radius, so that means that it's
let's see that's the part you got to be able to put it in words, right, AJ?
So since the radius of potassium is much larger, the distance between the electron cloud and potassium's nucleus is much greater, so
Yielding a
smaller
okay, lesser magnitude Coulombic attraction or lesser force of attraction, something like that. Very good. All right, so that would require to be less energy would be required to force that attraction apart or to break the attraction. All right, so definition of lattice energy, I've been kind of using it loosely to at least give you some context, but this is the exact definition. It's all about the gaseous ions. So in your book reading last night, you guys did ionization energy and electron affinity. You had to draw those little half reactions where you had gained or lost an electron. I don't know if you noticed, did you notice they were gases? Maybe you did. It's because it's referencing things in their gaseous state to kind of put everything on the same ball field. So energy required to separate a mole of a solid into its gaseous ions. So why are all of these positive, the way it's expressed in this statement? It takes energy, right? These are all positive. This is an endothermic process. It takes energy to rip a lattice structure apart. So if I flip this and I say energy when the lattice structure is put together, what would you think would happen? What would change? Say it again? It would just express the lattice energy is negative. So lattice energy is used loosely sometimes because it's just talking about the energy of the lattice structure, but it depends on how you describe it. If you're describing it as forming the lattice structure, it's going to release that energy. If you're ripping the lattice structure apart, it's going to take energy, hence positive. The previous example was negative. Tell me when you're good. Some of you guys are just absorbers. I was the person frantically writing notes going, hold on, professor, hold on. So just let me know. I'm just trying to make sure I get you the basics of everything. So here is an example of the lattice energy that we just spoke of. This, though, the way it's expressed is a sodium chloride coming together. Sodium ion gas, chlorine ion gas coming together makes solid sodium. How would you think that lattice energy would be expressed, positive or negative? Say again? Because ions are crazy ions, right? They're super, super duper reactive. If you have free radicals or free ions out in the world, they basically attack your insides and then they oxidize your insides. So what do you eat to counteract oxidants? Antioxidants, blueberries, blackberries, and things with anthocyanin. Okay, so these two ions are crazy. They come together and they form a nice, stable sodium chloride bond. So this should be a lattice energy of negative because it should be releasing the energy that are kind of the ions are comprised of. So we can't directly measure that. It's really difficult to ionize and capture those gases as they are and then force them to form a bond. It's just so difficult. So what we do is we try to calculate them based on other values. So other values that might be interesting would be, how do we get sodium into a gas? We're going to actually calculate this, so make sure you write these examples down. I'm going to show you the exact process on the whiteboard over there, okay? Yes, so sodium naturally doesn't come as a gas. You must sublime sodium, okay? Chlorine, you can see chlorine here as a chloride. Well, chlorine doesn't come as a singleton, it always comes as a diatomic. So we have to break chlorine diatomic into that molecule into two individual chlorine atoms. It's already a gas, so it's all good. What's BDE stand for? Anybody? I just said you have to take chlorine's molecule and break that bond. Bond dissociation energy. BDE, bond dissociation energy. We've done this before with delta H's, like in balls. Next one, you can see that sodium, making an ion, releases another electron. What is that? Yes, who's my ionization energy group? Yes, now you're confident. Yes, it's us. Okay. So that's the energy of ionization, meaning energy to take one electron from sodium and release it to the wild. Next one, chlorine gas achieves an electron. That's gaining an electron. A full-on gain of electron is who's my EA group? Electron affinity, right. So you can see that these are written oppositely, and our groups will be talking about this, but this is why I'm introducing it first, so you guys actually have some background with it, okay? And then lastly, heat of formation. Why the heck is this heat of formation, this reaction? Anybody? Do you remember what the heat of formation is? Heat of formation is the heat or the energy released when you form 1 mole of your product from its, I think, Levi, did you say it? From its elements. So it's elements in their standard state. So sodium in its standard state is sodium solid, right? Chlorine in its standard state is chlorine diatomic gas. So you'll notice that these look different than what they were before. But this is the solid sodium chloride forming, and that's a definition from delta H stuff that we did back in thermodynamics. Yes?
I was going to ask, I read the delta H EA is delta H the activation energy. Is there like...
There's no activation energy, it would be labeled as E sub A. This is EA. So, unless you're in your book, it shouldn't have said that there. I hope not, good Lord. Okay, so our job is we're going to use Hess's law, like we've done before with delta H's. We're going to put these equations together in a way that makes sense to make this reaction happen, and we're going to solve for the energy of that lattice energy. You ready? Let me put this down here so you guys can see. Is that in the way now? Probably. Okay, so draw a line at the bottom of your paper. I need that because I can't see if I move it. So write down Na plus on the bottom gas plus chlorine gas on the bottom yields NaCl solid. Okay, and our job is to find what this delta H is, which is the enthalpy of lattice energy. Okay, so remember with Hess's law, you can flip reactions, right? You can multiply them by coefficient. What do you do with the delta H when you flip a reaction? Switch the sign. What do you do with if you multiply by a coefficient? Multiply the delta H the same way. So equilibrium was the only funky ones that did different things. All right, so what equation do you know that we want to keep the same way it is? Give me any of them you guys want to start with. I'm going to start with the bottom one because I see that sodium chloride solid and I see it here. I'm writing it exactly the way it is. So write that at the top. I'm just going to start at the top because that's where I want to start. So there's sodium solid plus 1/2 chlorine diatomic gas yields sodium chloride solid. And that delta H is already, I need some space. That delta H is what? Negative 411 kilojoules? Okay. Alright. So I need to keep that. Don't touch that. I'm boxing it off so I remember that needs to stay. Now, I'm going to start with my sodium. I need to get rid of sodium solid, right? What does it need to become? Sodium ion gas, right? So what equation can I implement that would cancel out sodium solid? The sublimation one, okay? So I see sodium solid here. I'm going to put it over here because I need it to cancel, and that means sodium gas is here. What did I do to my delta H? Say again? Yes, you have to flip it. I just need some more space. Sorry. Okay, sodium gas yields sodium solid. That's a, oops. I have to line my work up, so I'm a little slow here. So solid. This delta H is, thank you. Okay. And then sodium solids will cancel, so we're in good shape there. What about this half chlorine gas? Do I want this? I do not want that. I want just chlorine ion at the end. So chlorine gas, I need to adjust. So let's go ahead and just take normal chlorine, chlorine diatomic. Do I want to put that on the left or the right? Right. And then I want to cancel half those chlorine diatomics out. So what's going to go over here? You just tell me. 2 normal chlorine gases, okay? Now, is this going to cancel? No. So what do I need to do to this reaction down here? Half it, right? So multiply by half. All right, so how have I manipulated delta H? Say again? Flipped it and divided by 2, right? So that was 243, so negative 243 divided by 2. Are you okay? All right, I just see confused faces. I'm just making sure we're good. All right, so chlorine is going to cancel just fine. I now got this. I got this sodium and I got this chlorine as a gaseous form. Let's go ahead and take sodium first, because I know that sodium gas is not what's existing at the end. I need to cancel that out. What equation do I want to use? The third one. How do I want to write it though? Flip it. Sodium ion gas plus 1 electron yields sodium gas. How is the delta H written? Negative 496 kilojoules. Okay? Now, that sodium's gone. That sodium ion remains. I'm going to box that off because I know I want to keep that. That's a negative place to go. Now, this chlorine gas that's here, I don't want it. What do I need to do? So take that fourth equation, flip it. So chlorine ion gas yields chlorine gas plus 1 electron. And I'm not manipulating, right, because I already can see that there's only 1 chlorine here, right? Half times 2 is 1 chlorine, so that's going to be just fine. Okay, and that delta H is what? Positive 349, great. Alrighty, have I used all the equations? Can we double check that we have everything we want? What else do I know I need to keep? I haven't boxed it off yet. The chlorine ion. Okay, so let's double check that everything has aligned and we can actually cancel like we do in Hess's law. Can sodium solid cancel? Yes, there. Can half of a chlorine gas cancel? Yes, because that's half and that's half distributed over, so that's half chlorine gas. Sodium gas? Yes. 1 chlorine gas? Yes, here and here. 1 electron? Yes. And what's left? Everything we wanted, right? Yay, we always get what we want. All right, so let's go ahead and calculate delta H. Calculate delta H for me. What'd you guys get? negative 788.5 kilojoules, right? All right, that should be the delta H lattice energy, or just the lattice energy. That's the energy given off when what comes together? Two gaseous ions come together to make it 1 mole of the solid product, the solid ionic product. So negative 788 should reflect what we had here. Where's sodium? What do we do? Sodium chloride? Sodium chloride? 788. There it is right there. Now, I told you before, though, this was expressed as positives because it was showing a... How was it? What was it showing? Yes, this one's the breaking down of the lattice structure, where we just built the lattice structure so it released energy through energy stabilization. Give me a double thumbs up if that made sense, 100%. Just one if you're like, I'm mostly there. Oh, right, okay. So this is an energy component of bonds, which we briefly talked about, but we're going to do bond dissociation energy again when we do Lewis dot structures, which is next week. Yeah.
Is this like a question or how long test?
Yes. Or I could say, what is the appropriate half reaction for the ionization energy of sodium? So I could ask you, what's the appropriate half reaction, meaning the one that shows this is not ionization energy, would be the other way. Sodium releasing an electron. So more definitional information too. All right, last thing I want to show you for now, binding energy. This is just a term to know. It's really relevant with one of my groups. I think you guys will figure it out. It's on the board. Which group? Raise your hand. That's you. Okay, ionization energy. I've been picking on you all day. All right, so, yeah, ionization energy. So this is just the definition. That's all I'm going to show you right now. It's going to be relevant for something we start talking about more next week called the photoelectric effect. But it's just the energy required to basically take an electron, to free an electron from an orbital. So we talked about this with my lovely people who ran away from home and got tattoos. So energy it takes to take you from an outside orbital versus the energy it takes to take you from an inside orbital. So if this is mom and this is me on my first energy level, or this is me in my later years on the 5th energy level, which energy level or which electron here or here do you think is going to take, or is going to require more energy to become free? Why? Say again? So close to nucleus doesn't give me everything.
Yeah, it has less energy already.
It takes more to break the attraction.
Okay, I like all those so far. Keep going. So it takes more energy to break this one free and set it free because it's got higher binding energy due to its proximity to the nucleus. Closer to nucleus, higher force of attraction, right? Basically Coulomb's law again. Yeah? Right. This one, less energy because it's farther away from the nucleus, so the force of attraction is lower. And I don't know if you read, I'm sure you read this, a little bit about shielding. There's all these energy levels in between. All those energy levels in between are blocking the positive, loving mom from their rogue teenager out here. So these negatives that are in the way don't allow that attraction to be fully felt. Okay, so that's why another reason, a secondary reason why the binding energy is lower here than it is here. And we will talk about binding energy with our photoelectric effect stuff next week. Okay, that's it for me. Are you guys okay to move on to your groups? You have about an hour, right? Okay, 15 minutes. 15 minutes it is. Go. Somebody catch Savannah up. That's all I do for now. Okay. Yeah. Energy level, 102, and then the second energy level is like 2s2, 2p2. So we had a little bit of shielding, there's only 1 energy level in the way. Going down to like iodine, there's 5 energy levels shielded and retraction from the nucleus to the outside. So iodine is bigger for 1 because it needs more orbital spin for a lot of electrons. 2, okay, it's fixed for your purposes. It needs orbitals to fulfill all the phosphorus electrons. Orbital spin this time. 1s2, you're not first energy level. 2s2, 2p6, you're the second level. 3s2, 3p6, 3p10. When they part, and every time you build, so how many energy levels are there? Right here, it's 0. Are you counting the last the transitions? Those are built, so you see what the 2 light ones are? Those built in there, so there's only 7.
What is it? Does it have a name? I just want to see what it looks like.
Darn, so you guys are listening to Ruchi, right? So then I guess for Ruchi, then figures okay for Sue.
Oh, I have a question.
I'm answering.
Did you send us in 3?
In title and nothing else.
Okay, I can switch to the order that you
Oh wait, I marked it with
Yeah, can you go back here in a second? I'm just only got 4 of them. So go to my extensions on my website. Has the Excel file. So tell me where's hydrogen at?
what is happening?
I don't know. The way that I would do it, you got like a white like behind the picture box. It controls it. There you go. You got stuff in there. Get rid of that. Or actually, that's pretty good. Century.
Yeah.
Not good. Unhighlighted.
Well, that's another thing I need to figure out how to make this.
Just snip it. Just snip it. You don't have snip on there? Here's the Bitly address.
So I remember you saying something earlier about how ionic radius has no like definite trend, but I remember I wrote something down about that. How it's like no definite trend when you're going. I think it was down.
but it's slightly more negative.
So one thing for sure, on the ion stuff, when you were showing the compounds at the bottom, it does have those form or same ions, and the parent atoms or sizes will drop. But of course, you're going to condition they're going to tell something about phase change. Sure, and trends will be less slow. Yours will look a different number of years of ions. So one thing you'll notice though is as you sit down, you just have an anion over here. There's larger, right?
Yeah.
So which elements predominantly form
I'm going around for clarification questions.
Is that because the sound we were just talking about that smaller atoms closer to the increasing
Okay, so do you want to do the definition of the next on the same slide? And then we can do, okay, and then we can do explanation and sections on.
You chose this?
No, we did draw.
Oh.
Like I grabbed with them. I did not pick this.
It's the energy associated with your
Sitting on your right here.
Like reverse, all the way down, like
why there's
so we also need to put yeah, like copy and paste everything, and then just take this
Oh, this is mine. It's all shiny.
This is mine. You have to read to seven? But the thing is, though, you don't have to answer. Because he came and he's like, I'm checking the annotations, but he's like, but you weren't here yesterday. You didn't get the reading. I was like, so really, because you weren't here, you don't have to read. Really hoping I'm not having some, he doesn't be like,
I found all this stuff online. I like paraphrase it. These are basically all the explanations behind. Yeah, I think
energy associated with addition of electrons. Not gas plus the electron.
Yeah. That is a block Bitly addresses now? We just used a Bitly address. Here, Savannah, I'll show you. My bad. I'm so sorry I made you wait on that stupid question.
Do you want me to make up the lab from yesterday, or do you want me to just like get?
Get data from Lucas and then do the questions. It says it's blocked. This is crazy. Hold on, I got you because I have the actual document. So I made this yesterday. Periodic table trends groups. Here you go, Savannah. So, where are you at? There it is. Guided notes, question mark, facts. So,
I can't.
PowerPoint.
I can't make the guided notes if there's no PowerPoint.
True that. You're making a that's a,
Oh, wait, it's a root sheet.
so facts plus PowerPoint. So I would actually maybe switch for now. Have you guys started a PowerPoint?
They started,
We
but they
started
didn't
it,
put.
but the root sheet hasn't put anything in it.
Okay, so then switch for now. I mean, instead of being unproductive, tell Arisha to do the guided notes after the PowerPoint's mostly made. mean, you guys still have 40 minutes to work, so definitely knock out some of that, Savannah, and then somebody text Sarush and say, add to the PowerPoint, and then start a guided note sheet.
Okay. So, this is right.
Change it this way.